Lognormal. In this model, the statistics of the irradiance fluctuations obeys the log-normal distribution. This model is characterized by a single scattering event and is best suited for weak turbulence regime. The PDF can be given as, where sigma I2 is the write-off variance, IB the field irradiance in turbulent medium, while the intensity in free space, no turbulence, is represented as I0, and A is the mean log intensity. Negative exponential. In this model, the number of independent scattering is very high and it can support for saturation regime. Therefore, the irradiance fluctuation follows the Rayleigh distribution, entailing negative exponential statistics for the irradiance. The negative exponential PDF can be given as, where A equals I0 is the mean received irradiance. Gamma gamma. The atmospheric turbulence is modeled by gamma-gamma distribution with scintillation parameters alpha and beta, which are indicated as functions of the write-off variance and a geometry factor. The PDF of the gamma-gamma channel model is given by, where alpha and beta are the effective number of large and small-scale turbulent eddies, gamma asterisk is the gamma function, and k alpha minus beta is the modified Bessel function of the second kind of order, alpha minus beta. The effective number of large and small-scale turbulent eddies alpha and beta for a spherical wave is given by, where d equals kd2/4 liters, k equals 2 pi, lambda, is the optical wave number with lambda being the operational wavelength, L is the length of the optical link, and d is the receiver's aperture diameter. The parameter delta N2 is the write-off variance and is given as, delta N2 equals 0.5 Cn2 K7/6 L11/6, and the Cn2 represents the refractive index structure parameter. This model is valid for all turbulence regimes from weak to strong, and the gamma-gamma distribution approaches negative exponential distribution when it approaches saturation regime. M distribution. The transmitted signal is scattered due to natural turbulences such as rain, fog, smoke, smog, and heavy dust particles in the atmospheric channel, AC. The combined effects of fading due to atmospheric turbulence and misalignment are considered in the combined unconditional probability density function, PDF, for M distribution has been derived in. As derived in, the PDF of the irradiance H is given by, where mu equals 2b01 minus rho is a large-scale scattering parameter, beta is the quantity of fading parameter, A0 is the fraction of the collected power at R equals 0, radial distance, ohm equals ohm plus 2 rho b0 plus 22 rho b0 omega cos phi minus phi b the average power. The amount of scattering power coupled to the loss component is denoted by the parameter rho and its range from 0 to 1. The parameters phi a and phi b are the deterministic phases of the loss and the coupled to loss component. The parameters g, a and ak are defined as, where sigma s is the Poynting error displacement standard deviation at the receiver, WSIC b the equivalent beam radius, and can be calculated by using the relations v equals pi a/2 wz, WSIC equals wz 2 pi erf/2 v minus v2, where wz is the beam waste at distance z, a is the radius of a circular detection aperture. The gamma-gamma, k distribution, and negative exponential model are obtained by the values of the parameter rho equals 1 ohm equals 1, rho equals 0 ohms equals 0 or beta equals 1, and rho equals 0 ohms equals 0 or alpha, respectively.